Hello, this is Dr. Viv. I will be talking about differentiating under the integral sign. This is a very important technique in mathematics, and it's very useful to evaluate complicated integrals. Now, if you observe that an integral in one variable can actually be considered as an integral with a free parameter, which in this case is called y, and it's somehow easier to integrate the differentiated value after you differentiate with respect to y or some other parameter, you find that the answer is much easier to evaluate than the original integral. Then you can always use this. The great physicist Richard Feynman used this a lot to evaluate seemingly impossible integrals, and so this is sometimes called Feynman's trick these days. Even in the mathematics literature, it's sometimes called that. But this trick was known to all the great mathematicians of the past. Like Euler and Gauss, they definitely knew all these things. Lagrange actually proved it using his mean value theorem. So the proof of this can be found in advanced texts of calculus. I won't be bothering with proving this, but rather just learn how to use it. So in the previous video, we actually did a pretty complicated integral using what's called a half tangent substitution. That integral I called I of a comma b. Let me reproduce that here. It was the integral. It was the integral which was not exactly between any limits, so I'll just write that first. And I called it x. I didn't call it x, I called it theta, but now I'll call it x in deference to this notation. The integral we looked at was integral dx divided by a plus b cosine x. Now when we use the half tangent substitution, we got the following result for the case a bigger than b. I'll just deal with that case. As an exercise, I invite the student to reproduce everything I do in this video for the other case, that is for the a less than b case. That would be an excellent way to understand the material of this video. So 2 over the square root of a squared minus b squared arctangent of the square root of a minus b divided by a plus b times tan of x over 2. And because this is a definite integral, I also put a plus c there. Indefinite integral, I put a plus c. Now, even though this theorem, differentiating under the integral sign, does not technically require us to have limits, for the sake of presentation, I decided to have limits because it's easier to show you these things in a simpler fashion. So when I put the limits of 0 and pi, let's see what happens to this complicated result. Well, first of all, the tangent of pi over 2, when I substitute for upper limit, I'm going to get tangent of pi over 2, that's infinity, times a real number, because a is bigger than b, this whole thing is a real number, is going to still be infinity. And the inverse tangent of infinity is pi over 2. The lower limit yields nothing because tan of 0 is 0 and the arctangent of 0 is still 0. So I'm going to end up getting pi over 2, and that pi over 2 will cancel the 2 in the pi over 2 will cancel this 2, and so the answer ends up being pi divided by the square root of a squared minus b squared. That's certainly a result that we can do something by using this technique because it's easy to differentiate this. Now, in order to figure out what you can do with this, let me try to evaluate two integrals. Let's suppose I'm interested in evaluating I've already done the hard work here, and then someone comes and tells me, hey, an application came up and I want you to evaluate the integral from 0 to pi of dx over a plus b cosine x, but squared. Okay, and another integral also came up, and that is the integral from 0 to pi of cosine x dx divided by a plus b cosine x squared. Let's take a step back and see how these two integrals are related to the integral that we've already done. Now you can get 1 over a plus b cosine x squared by differentiating this one with respect to a, because when I differentiate with respect to a, considering b and cosine x to be simply constants, the derivative is going to be 1 over this quantity squared times the derivative of a, which is 1. And so you'll get this by differentiating this with respect to a. Similarly, you'll get this result by differentiating this result with respect to b. By the same reasoning, a and cosine x are now constants. So when I differentiate with respect to b, I'm going to get 1 over this whole thing squared, and then times the derivative of b cosine x with respect to b. Well, that's just cosine x because b gets differentiated. Okay, so that's just cosine x. So that in that following way, we can actually do these two integrals. Now what I'm going to do is, just to make sure that you understand the process, I'm going to call the function f here of x comma a is equal to 1 over a plus b cosine x, and I'm going to call a function g of x comma b equals 1 over a plus b cosine x. Well, they look like the same function, so what's going on? Here I'm going to regard this function as a function of x and a function of a, because I'm going to differentiate with respect to a and get there. Here it's a function of x and b because b is given importance, because I'm going to be differentiating with respect to b and get that. Basically, it's the variable y in each case. The variable y in the case of the first function is a, and the variable y in the second case is a variable b. Okay, so now let's see what we get. By applying this theorem, the integral I1 is just del by del a of what I called I of a comma b evaluated between 0 and pi. Well, that's just that result. So that's, I'll pull out the pi there. So pi times del by del a of 1 over the square root of a squared minus b squared. Well, that's not a difficult thing to do at all. All I'm doing now is differentiating, pretend that b is a constant. So this is pi times, now this can be written as a squared minus b squared to the power minus half, and when I differentiate it, I'm going to get negative half times a squared minus b squared to the power minus 3 halves. That's how differentiation works. And then I go inside and differentiate with respect to a. So using what's called a chain rule, that's going to be 2a minus 0, because remember, in this partial derivatives, b is considered a constant if I differentiate with respect to a. So now all I have here is a cancellation with 2, and the negative sign is still there. So that's negative pi a divided by the square a squared minus b squared to the power 3 halves. We have solved the first integral, I1, through nothing more than differentiating an already established result. It's pretty efficient. I2, by the same token, is del by del b of I of a comma b from 0 to pi, and this time, instead of differentiating with respect to a, I will differentiate with respect to b. So this is pi del by del b 1 over the square root of a squared minus b squared. The only difference, I won't repeat this, because the only difference between this and this is the factor b. Okay, now when let me just go ahead and do this. It's not too much writing. So this is minus half a squared minus b squared to the power negative 3 halves times, this time a is considered a constant, so it's 0 minus 2b. And the only difference now is that the minus sign disappears because minus of a minus is plus. That 2 still cancels. So I'll get pi times b divided by a squared minus b squared to the power 3/2. Well, in this manner, we have evaluated two seemingly complicated integrals without so much as sweating, because all we did was differentiate something. Now, integration is much harder than differentiation. All your techniques of integration are there, but you hardly have any techniques of differentiation other than quotient rule and product rule, because differentiation is so easy. And this is what makes this technique such a lovable technique in physics and mathematics, because once you've done the hard work for one integral, you don't want to keep doing that. I mean, each of these can be separately solved by half tangent substitution. Okay, if you were not given that integral first, but you were given this integral first, well, that would be a pretty sad day, because you will have to use the half tangent substitution on something that's slightly more complicated than that. You will still get this answer at the end of the day if you take the limit 0 to pi, but it'll be a much longer process. Here, since you already have the result worked out for the simplest case, so one of the lessons to be learned from this is, when you want to evaluate an integral, someone gives you a complicated looking integral, okay, always evaluate the most basic, the seed atomic case. Okay, we'll call this the atomic case. Once you have the atom established, you can get the more complicated results by simply differentiating this atomic case repeatedly with respect to some variables. Now, by the way, if you don't have this a and b handed to you in a platter, what will you do? Suppose someone asks you to integrate the following integral. Integral 0 to pi dx over, let me make sure a is bigger than b. So 5 plus 3 cosine x to the power 7. Okay, if someone gave you that, well, you clearly know that you have to repeatedly differentiate with respect to a, but I don't see a anywhere. So you have to just be bold about this business. You just do del by del 5, okay? Or if that makes you uneasy because 5 is not a variable, you can call it a and b, and then at the end you can put a equals 5 and b equals 3. All right? So I just want to show you how to do this. So if you do this once, you're going to get to the power 3/2. So all you've got to do here is to keep repeating the process 7 times. But each time you repeat the process, you're going to get factors like these factors, exponential factors. So it'll be 1 over 7 factorial. Okay, so you have to adjust for factorials here. I would urge you to try something like this. It's a really fun exercise. You just have to keep differentiating this over and over and over again, and then that'll be the answer. And I think the other exercise I would like you to try is the one I mentioned earlier. Repeat all this for I of a comma b from 0 to pi for the case of a less than b. That's where you get the ratio of two logarithms instead of the inverse tangent that you get in this problem. And try these companion integrals for that same case.